Okay, so now I'm going to introduce a few very simple models. We'll start simple and then make it a little bit more complex. For some of you, that might be too slow because you know these models, you've seen them before, and for others, it might be too fast. But hopefully, overall, everyone will benefit. As Paul said, it's hard to get it right with this kind of diverse background that you all have. So we'll start with a very simple model. Just some population, we can think of it a population of pathogens, but as I just told you, a lot of these can be applied to all kinds of settings, such as the population level. So you can think of this as humans as well. So just some population of something that can grow and die. So a very simple model. And so we'll implement that initially in a discrete time equation because it's usually a little bit easier to understand. We'll then later switch to a different formulation. So we have these population P of, I'm calling them pathogens for now. And so we have the pathogens at some time t. And then what they do is they grow at some rate and they die at some rate. And that tells us then the combination of those, what happens at the next time step t plus dt in the future. So you would start with some p at some initial time. Usually we choose t equals 0, but that is pretty arbitrary what time you start. And then if you know the growth rate and then you know the death rate and you define a little time step, then you can move forward. So notice here, there's these processes explicitly modeled. Of course, very simple, but you have the growth process as an explicit one and the dying process here in the model. So it's a mechanistic model with the two mechanisms of growing and dying. So just to get a little bit of an intuition of how these models work, you can try it for yourself. If we started with 100 individuals at initial time step, we had a growth rate of 12, so G was 12, and a death rate of 2, so DP was 2. And we took time steps of 1. So how many individuals would we have after 1 time step, 2, 3 time steps? Try it real quick and then type it in the chat. Okay, let's step through it together. So we start with 100 here for PT. So then we have G times PT, that's 12 times 100, minus 2 times 100. So that's 10 times 100. That's 1,000 multiplied by the time step of 1. So that's 1,100. That's after the first time step. So Carla just posted that. So if you start with 100, after the first time step, you have 1,100. Then you put it again, 1,100 here. Then you multiply 10 times 1,100. So that's 11,000. And then plus 1,000, so 12,100, right? I hope I did that right. So they grow pretty fast. That's exponential growth. And you have a very high growth rate. But so this is how you would basically, if you didn't have a computer, you would solve that by hand. Someone would tell you, we have this many at the start. This is the growth and the death rate. And then we're stepping through in time. And you could do that now by hand. It's tedious, but you could do it. And this way you could then, if someone asked you, how many are there going to be 10 time units from now, you could figure that out. So you could make a prediction if you had this death and this growth, how many pathogens would you have after 10, whatever these time units are. Could be hours or days. Yeah. Make sure you revisit it if it wasn't quite clear, if it was too fast, but try to just plug in the numbers and then you do it and you do it again and you do it again iteratively. Let's play with the model a bit, just to get a bit of an intuition how those work. So on the top is the model I just showed you. On the bottom is an alternative. You see the difference is here I have G times B, P, and here I only have G without multiplying by the P. So if this is equation, what's the difference in words? So it's the first, and then is this a good model? You can either type in the chat box or you can unmute yourself and say something.
The growth doesn't depend on the population. It's probably not a good model for most. The second one.
Yeah, so the growth does not depend on the population, or another way of saying it, it's not exponential growth. It's instead linear growth. When would that be maybe a good model? When would that not be a good model? Or can anyone think of a situation where it might be an okay model?
Maybe if you're being given like a drug or something and it's being given at a constant rate, or there's a constant influx of population and there's no reproducibility within that population.
Yep, something like that. And in the chat, people saying the same, like growth comes from outside or importation. Yeah. So, let's assume it's T cells and they're cranked out by the thymus at a constant rate. And so this is independent, maybe to first approximation, how many T cells are currently there. The thymus just cranks them out at a current rate. So that could be an instance where that bottom version of the model might actually be the better one. Now, if we want something like a dividing population of bacteria or a dividing population of active T cells, then the exponential growth, the top one, would be the better one. So you want to think of, okay, what's the biology of the process I want to model? And based on that, you would then pick the way you think it's best represented in a model. In this case, both of them could be reasonable based on what you're trying to model. Here's another one. Now I left the growth term alone, but I changed the death term. So again, in the top, it's dependent on the population. In the bottom, it's not. So what's the difference here, and is this a good model? Or can you think of a situation where this model could apply?
So the problem with that model is that you could end up with negative because you have a constant amount of death.
Exactly. So this is a bad model no matter what, because the problem is that you could have no pathogen, 0. So this would be 0, this would be 0, and then you would have still death. Well, you can't have things dying if no one's there or nothing's there. So this isn't just a bad model. There's no biological time when this will apply, that if there's population is 0, you can't have any death. So some models are just bad no matter what. It's not a good way of formulating the model. And some models can be good or bad depending on the situation. So I just wanted to show you 2 examples. And this also is a good thing to keep in mind. If you're building your model, you want to test it, it's always good to look what it does at the extremes. So basically here, what happens if nothing is there? Does the model behave like it should? What happens if this thing is really large? Does the model behave like it should? So if you test it at the extremes, that often gives you a pretty good insight of, does the model kind of behave the way I think it should behave? So I started with the discrete time model because it tends to be somewhat easier to wrap your head around it. And those models are useful when you have sort of a natural time step. Let's say you have bacteria that divide at very specific times. It's also often used if you have very complex simulation models. For instance, the one I showed earlier with the influenza spreading in the US. That's such a complex model that just for computational reasons, you have to use discrete time steps. For the models, we'll be looking at these what's called compartmental models, where we just track the total number in a population, total number of pathogens, for instance. The continuous time models are more common. The reason for that is even though any bacteria or pathogen might divide or die at a certain time, in the population as a whole, there's constantly birth and death going on, so it's often better to describe it by sort of a continuous process. And if you have a continuous process, you tend to formulate these models as ordinary differential equations. And those are the models we'll be focusing on. If you move from a discrete time model and make the time step rather small, then you'll actually end up at the continuous time model. So here's, if you've ever taken calculus, you've probably seen something like that, where they start you out like this, and then you rewrite it, put all the things that have to do with the pathogen and the time over there, and then you move the time step to really small, and then you end up at the continuous time model. When you think about it, a computer can't take infinitesimal time steps. It actually has to take discrete time steps, even though small ones. So the computer basically does something like this up there, just a smart way of doing it. It doesn't implement it exactly that way, but something of that sort. You can write the continuous time model in different forms. The top one is the most explicit. It shows that the quantity P depends on time. Since in pretty much all of our models that is the case, we're usually lazy and we drop that. And the one below has the dependence on T gone, but it still shows the dP by dt. And the most common one is just further shorthand where you put the dot on the p. That means the change of that variable with time. So the way you read it is, on the left side is the variable that changes over time. And on the right-hand side, it shows you how it changes the different processes. So these processes on the right side, they represent the mechanisms you're interested in. Of course, often simplified. But those are the ones that you think are important for your system and you want to include. So a positive term means it describes increase in this population, and a negative term means it describes decrease in this population. Or inflow and outflow is often also used. Of course, depending on the variables, the parameters, they can turn positive or negative, but almost always in our systems, they tend to be positive, because if you assume this is the growth rate, well, we'll assume a positive growth rate. Otherwise, if we're negative, it would be sort of the death rate then. So quite often the way we formulate our model, we think of the parameters as positive and representing a certain process. Though it doesn't always have to be the case. So let's play with that model a bit more. If you had this model now, for some of you that might be obvious, others might not be, but try to think about it. If you had different values of G and dP, what kind of results would you get for P if you ran the model long enough? So we already looked at one where you started with P at 100, you had G 12, dP 2, and we saw it kept growing. So any kind of combinations you can think of G and dP, what kind of patterns can you get? Again, you can write it in the chat, or you can just say it. Yeah, so if you have exponential growth, they go to infinity. And then another one was here, 0. So yeah, if you have G smaller than dP, then you get decline and you end up at 0. And there's one more option, one more pattern you can get. You can get either that whole thing go to 0, the whole thing go to infinity, or it could be constant exactly. If G is exactly equal to dP, then whatever you start out with, that's what it's going to be, because the growth and the death balance each other exactly. Now that's of course very unrealistic for real world systems. You never have two things exactly equal. So in the real world, if we had this, we would either see growth or decline to 0. Now decline to 0 is reasonable, if you have higher death, but growth up to infinity is unreasonable. Exponential growth is positive, but eventually we know it has to level off and slow down. So if we want to do that, if we want to make the model a bit more realistic and say, okay, exponential growth is okay, but at some point we want to level off, and when we reach some high level of P, how could we do that? Think about it real quick. If you know the answer, you can type it in the chat box. If not, we can, after you thought for a second, can look at it. All right, there's the perfect answer there. So I'll put it up here, what Zizhang suggested. So we can replace or add to the growth rate a term that slows it down when the pathogens reach some kind of level. So that's what we did here. So what you get here is that if P is pretty small compared to whatever that P max is, some value, then this is basically almost 0, this term back there. So then we have G times P times almost 1. So we have the exponential growth that we're looking for. But now as P approaches P max, this term goes close to 1. So we have 1 minus something that's almost 1. So that whole growth term here is being reduced and slows down. And if P is exactly P max, then this whole growth term is 0. So then this way we can basically slow down the growth in our model when P reaches some level. If P starts out greater than P max, then we actually get decline. So this term is then negative in the back here, in the front, and of course this one too, and we decline. And you can, from this, see when the population settles down is when the growth term balances the death term. So when GP 1 minus P over P max equals dP times P, and you could solve this now for P if you want, and that will actually tell you, without having to do any simulations, you can just do it with pencil and paper, compute this what's called the steady state, the level at which P settles down, no matter what you started out with. It will always settle down at that level. Okay, so that we stuck in a little bit. We gained some realism instead of exponential growth. We now have growth that saturates, so that's a good thing. We had to pay for that realism with an additional parameter. So we have now this P max in there, and the equation got a little bit more complicated. And that's the general trade-off you see when you build models. For any additional realism you want to stick into a model, you usually have to put in more processes, means more parameters, the model gets more complicated. And of course, you need numeric values for all these parameters to be able to run it. So that is always the tension you have in these kind of models. And the trick is to find the right balance to get a model that's complex enough that it has the details you're interested in, but not so complex that you basically have something that is too unwieldy to understand, or you need a lot of data to specify the parameters that you don't have. So that's always a tricky part when you build models. Okay, let's move on. We started with a single variable model, but that's kind of boring. Even with the saturating model, not much is going on. It gets interesting, and that's where these kind of models really shine and are useful when you have multiple entities, variables, or compartments that are interacting with each other. So let's put a second variable in there. Let's assume that P is some population, could be bacteria, could be something else, and then there's some attacked or consumed by some predator. Since I already took the letter P, I can't use it for the predator, so I'm just going to use H, and later we'll rename it. So now I have another entity that I want to track, so I need to give it its own variable. So we're now tracking the change of P over time and the change of H over time. And so, of course, we want to let them interact. So we assume that the predator here attacks and eats the prey P. So if we know that is sort of the biological process we want to implement, now we have to figure out how to put that in equations. So basically, what should we write down there for that equation, for the question mark in our top equation? So right now, we're just trying to figure out something for the question mark. Okay, so there's a suggestion, minus KHP. So basically, if we put that in, let's put it in. What that means in words is that the H, the predators bump into the P, the prey, at some rate K, and basically eat them. It reduces the P population because there's a minus sign. So that's sort of the term we've implemented now. H attacks P and at some rate reduces it by destroying it, if it were T cells, by eating it, if it were animals, you name it, but basically some reduction process. So that's that one. Now, of course, we need to let H give its own dynamics. So we probably need to let H grow, and we need to let it die. So if we want to say that the more P there is, the more the predator will grow. So how could we put that in a growth term? And then the same, if we want to have H a certain lifespan and then die, how would we model the death term? Any suggestions for the question mark for the H equation? Okay, there are two suggestions. Basically, twice the model the same. We make the H growth proportional to P multiplied by some constant. So that's this term here. This is the growth rate, and then it depends on how much P there is. If there's no P, then the H can't grow. And if there's a ton of P, then they can grow a lot, basically by eating them, or somehow, if it were, let's say, the immune response, it gets more inflammatory signals or stimulation signals and might grow. And then it has a certain half-life, and the inverse of that is this rate here. So DH is the rate at which it decays, and then the way you translate that to biology is you flip it around, and 1 over DH is then the average lifespan of H. And so just so you can compare it again, here's the same model, the discrete time version. So I did not the reverse of the process. I disentangled this and moved the PT and the DT to the other side. So for a small enough time step, these will give you the same results. Once you make the time step larger, and large depends on the other parameters in the model, you might see that they differ. And that model is, some of you have probably seen it. It's very well studied in ecology, called the predator-prey model. So P here is the prey and H is the predator. And there are many variations. This is the simplest one, but one could assume here saturating growth for the H. One could assume sort of saturating killing and different versions of that. And we'll touch on a few later. In terms of terminology, there's the unfortunate fact that what you call these things is really arbitrary. So you can name them yourself. The downside is that you always have to look very carefully. So if we want to think of bacteria and immune response, we just renamed this now. It's exactly the same model as this one. I just renamed P and H to B and I, and also gave a few other model parameters different names. So what that means is if you read the literature and you see a model and you look like, oh, this is a strange model, I've never seen that. Look carefully again. Maybe it's actually a model you know. It's just they use different letters. And it's also important to then note that if you use G for growth, that doesn't mean someone else does. Maybe they use G for the rate of killing here. So always look carefully, and it should be clear. There should be a table somewhere that specifies what each parameter means. Just make sure you read carefully, otherwise you might assume that they're using a letter for something that they end up not, and that could confuse. So always look carefully. And the same when you write the models, be very clear in what different letters and mean in your model. It's always a good idea, no matter how advanced you are in your modeling expertise, to use diagrams. Especially if you started out sketching it down, it's always a good idea to have diagrams. You basically have boxes for every component you want to track, and then you have sort of arrows going between them to illustrate what's going on in terms of interactions and processes. And then what you want to go is you also always want to go from your verbal description of saying, okay, I want to have bacteria grow and then exponentially initially and then saturate. So that's your verbal connection. Then you're drawing that in a diagram, and then you're trying to write it down in equations. And then you go back again and say, okay, these equations, do they correspond to the diagram and do they correspond to the words? And so going back and forth between that, usually initially you'll have to make a few iterations to make sure you get it all right, that what you plan on implementing in terms of your biology is actually what you put into your model. With experience, that will get easier and faster, but it's always good to use diagrams in between, even if in the end you formulate it as a differential equation. If you make something more complex, like an agent-based model where you can't even write down equations, you can still draw diagrams. So they're always useful to sort of illustrate the processes and what's going on in the system. So once you have your model built, you can explore it. You can sometimes do some math on it. We won't focus much on that because it's only really possible if you have simple models, and ours get complex quickly enough. But you could try to, mathematically analyze some of that. You can always implement them in some kind of computer program and simulate them. To do that, you need to basically say what the values of all these parameters are you have in your model. So you need to get them from the literature, and that can actually sometimes be quite tedious, especially if you try to study a system that's not well studied. It might be really hard to figure out, okay, what is actually the growth rate of this pathogen and what is the lifespan? And then you also need to specify starting conditions for the quantities, and then you can simulate it. So in this figure here, there's two settings, B1, I1 gives you one setup where the bacteria and the immune response jump up and down. And then you get another one, B2 and I2, for different choices of the parameters where they basically reach sort of a steady state that might be sort of a very simplified version of the TB model we looked at in the previous set of slides. Okay, then I'll move on. And you can always, if you have some later, put them in the Slack channel. In the modeling channel is probably the best one for those kind of questions. So I'm not spending that much time on that, and you will explore it yourself, this model. But this is now an equivalent, very simple virus infection model. And in fact, this is so simple, it doesn't even have an immune response. The other one had one equation for the immune response. Here we start out with no equation. But you can actually still get patterns from this model that look like real infections. So you have uninfected cells, infected cells, and virus. And so basically, In the absence of any virus, you have uninfected cells that are produced at some fixed rate. So here we don't assume exponential growth. We just assume they're basically pumped in at a fixed rate. That was similar to the earlier one where we just had G, or not G times P. So we're assuming just produced here at some rate N. And then they have some half-life or some average lifespan and then decay at some rate. So that's going on even if there's no virus around. And then if virus comes along, it can infect cells at this rate here. So virus bumps into uninfected cell at some rate B, and that leads to them becoming infected cells. Infected cells produce virus, and infected cells also die. They can die at a higher rate than the uninfected cells because they're stressed by the virus. They might be killed by the immune response, so they die faster. And then virus has two options. It can either be removed or decay in some way. That could be immune response, mucosal clearance, who knows what. Any kind of process basically that removes the virus is modeled here in a not very explicit form, and we could of course make that more detailed for any specific model, but here it's just some removal term. Or it could go on and infect more cells. So these are the processes that can go on in this model. We now have 3 variables, 3 compartments that we check, and on the right-hand side, you see the processes. So if you count, you have 1, 2, 3. This is the same process. 4, 5, 6. And this is kind of the same one, 2. There's another G here because you might need to convert units to make them work out right. So if you run this model, again, you can get different results. If you don't have any births and deaths of uninfected cells, you just get something that can look like an acute virus infection. So a virus comes along, you get sort of an outbreak within the host, and then your uninfected cells drop enough that you don't have any more left, and then your virus decays. If you have production of uninfected cells, then you can get something that's more like a chronic infection. So, think of the first one, the solid one, something like flu, or probably COVID-19, and this one here, maybe something like HIV or HCV or something of that sort. Very simplified, but the broad overall patterns you can get. And you don't even need an immune response here to get this. Now, is this a realistic model? It depends. Probably not, because you see here the uninfected cells, at least in the acute infection, drop down to close to 0. So let's say that we're flu and it were to destroy 100% of your lung epithelium, you would probably be dead. So it's unlikely that it's actually the depletion of the uninfected cells that controls the infection for something like flu or probably pretty much any respiratory infection. So while it can reproduce patterns that we see, it's probably not biologically realistic, and we need to stick in some immune response. Just one more side comment, I made it before, notation. So these models are exactly the same again as this model before, completely different letters, they look different. So when you look at models, just be careful to read them in detail, and you might realize that you actually know the model, you just are not used to their nomenclature. Unfortunately, there's no real standard. It's not as standardized as what you know if you know sort of the epi modeling, where we have the SIR model or the SEIR model. It's much more standardized there, though not perfectly either. And within host modeling, it's much more all over the place. So you just have to sort of look carefully. I'm spending 1 or 2 more minutes on an extended model that now includes some immune response, just to show you how it could be included. And you've learned in that whirlwind tour from Paul that the immune response is very complex, and of course we still haven't fully figured it out, and there's lots going on, and there's no way we can build a model that has every detail of the immune response. It would just be too unwieldy. We can still build models and try to get models that have the right balance between being realistic enough that they have the components we're interested in, and still be simple enough that we can actually study them and explore them. So here's one step. I'll sort of just an illustrative how you could do it. We'll do the virus model. We have the uninfected cells, infected cells, of virus. And now we throw in a bit of immune response. We have an innate response. We just model that with one term. We're saying this is the totality of the innate response, sort of all summed up together, so it doesn't correspond to any one specific biological quantity, but it's kind of the totality of the innate response. Then we have CD8 T cells, B cells, and antibodies. And so each component we track gets its own box. And now you see there's a lot going on here. All these arrows show interactions and basically who's affecting whom and who's talking to whom. So you can see this is like it was before, uninfected cells, infected cell, virus. But now you see the innate response here is induced by virus. The innate response then reduces production of infected cells. It stimulates T cells and B cells. B cells produce antibodies. Antibodies can kill virus. T cells can kill infected cells. So there's a good bit going on now, even though it's still obviously a simple model because there's only one innate response. There's no CD4 T cells. There's tons of stuff we don't have in there, but it's already getting kind of complex. And so that's sort of the challenge when you build these models. They can get complex pretty quickly, and you have to figure out when to stop. And what is the right amount you need for your model? And that's often there's some trial and error in that. And I usually recommend start simple and then slowly build up to more complex ones. Here are the equations. So it's already 2, 4, 6, 7 equations, and you see a whole bunch of processes on the right-hand side. I'm not walking through them because you'll be exploring this yourself in more detail with the DSRM package, but just wanted to show you it can get complicated quickly. Okay, and this ends the first introduction to modeling session. Any questions on that second part or anything that I've covered so far?